In the last video, we talked about how the planetary model predicts the relationship between energy and distance from the nucleus for an electron within an atom. To really probe that relationship empirically, light is a very valuable tool to use because we can use light with a huge variety of energies to probe a variety of possible energies that the atom could have. So in this video, we're going to learn more about the nature of light and how we can use it to interact with matter in a strategic way. Now, the classical model of light says that light is a wave. It's an oscillating electromagnetic wave. On the diagram here, notice that we have the electric field drawn as a red vector, and we have the magnetic field, which is perpendicular everywhere to the electric field, drawn as a blue vector. As a light wave moves through space, that's the purple vector here, the electric field goes up and down and down and up and down over and over and over again, right? And the magnetic field does the same thing in a plane perpendicular to the plane of the electric field. We've seen waves before in discussions of periodicity, but for the purposes of understanding light, we use terminology that's a little bit different. So rather than talking about the period, since the wave is actually traveling through space, the distance from, say, one crest to another crest is known as the wavelength and not the period. This is a distance in space. For light, this can span a huge range, as we'll see here shortly, and that's denoted using the symbol lambda. The speed with which the entire wave moves through space is known as the speed of light and usually denoted with the letter c, and you may be aware that this is somewhere in the neighborhood of 3 times 10 to the 8th meters per second. Extremely fast, which is of course consistent with our empirical experience. When it comes to light waves, we can also talk about the number of waves passing a particular point per some unit of time, and that's known as the frequency, which is usually given the symbol nu, which looks kind of like a V, like this. The frequency is measured in per second or hertz, and it's the number of waves, or what you'll hear sometimes referred to as the number of cycles per second. Frequency is cycles per second. Since cycles is just a unitless counting sort of thing, we usually just represent this as per second. And a fundamental relationship for all waves, which you see at the bottom of the slide, is the wavelength is equal to the speed of the wave divided by its wavelength. The speed is measured in, say, meters per second, the wavelength in meters, divide meters by meters per second, and you're left with per second. So this is the classical model of light. The essence of this model is that light is a wave. That's very important to understand about the classical model of light. Light does things that waves do. Wavelength and frequency and the energy of light can span a massive range. So this slide gives you a feel for the different wavelengths, for example, that we can see. Radio waves, which are the waves that literally the air waves travel on, are up here at 10 to the third, 1,000 meters, 100 meters, 10 meters, 1 meter. These are radio waves, so about the length of a person, a house, a soccer field, what have you. Microwaves come next, and they're in the 0.1 to 0.01 to 0.001 meter range. And of course, these are the waves that we use to heat food. Infrared is a little bit lower than that, followed by the visible, which is right around 10 to the negative 6 meters. And then we have X-rays in the nanometer range. And then further out from there, we have the harder X-rays, the higher energy X-rays, and gamma rays, which are massively energetic and very short wavelength rays with wavelengths around 10 to the negative 12. The frequencies, which are down below, can be calculated directly from these wavelengths, and give this a try to verify the relationship between frequency and wavelength. This will help you see also how the speed of light bridges the gap between frequency and wavelength for a wave of light. This last row, the energy of one photon, we haven't really looked at yet, but when we deepen our understanding of light here in a second, this will become more clear. What are some of the wave properties of light? Well, the big thing that waves do is interference, the addition or subtraction of two waves that are overlapping in space. There are two types of interference, constructive and destructive. Let's think about a hypothetical wave and another wave that's actually running with that wave in space so that the two are in phase. What happens when these two waves collide? Well, you can try this in your bathtub at home, right? And what you'll find is that the resulting kind of product wave has double the amplitude of the starting wave, right? Something like this. Same frequency, same wavelength, just double the amplitude. It goes up higher and it comes down lower, kind of thing. This is what we call constructive interference. The two waves are reinforcing one another to produce a larger wave. Destructive interference occurs when waves overlap in an out-of-phase way. So to see what that looks like, let's draw a hypothetical wave here and another wave that's now out of phase with the original, such that the trough of a red wave corresponds to the crest of a black wave, right? And so when we add these two together, if we imagine the zero line kind of as this line right here, when we add these two together, we end up with cancellation, right? And so the so-called product wave from this is just a flat line. There's no amplitude anywhere. That's what we call destructive interference, hopefully for pretty obvious reasons. The two waves are destroying one another because they're overlapping in an out-of-phase way. The combined effects of constructive and destructive interference create diffraction, which is the spreading of a wave when it travels through small spaces. And we will see this idea that waves can overlap with one another again. In fact, when we talk about the nature of the electron, we'll talk about the wave function and the concept of the wave function as a probability wave. Wave functions engage in constructive and destructive interference just like waves of water or waves of light do. So let's expand on this idea of diffraction a little bit more. How does diffraction work? When a wave passes through a space that's much smaller than its wavelength, at each place where the wave can sort of sneak through, we get this sort of circular or spherical spreading of waves outward. That creates points where the waves interfere constructively, say where these sort of field lines overlap each other, and where they overlap destructively, kind of halfway between the field lines. Where the waves overlap constructively, we see bright surfaces like this, and where there's destructive interference, we see shadow, essentially. We see nothing. Now, eventually, this will start to fade out as we move outward because the waves diminish as we move outward from the place where the light comes through. In the first experiment of Chem 1000, you'll actually see diffraction in action and learn how the distances between the centers of these bright spots allows us to calculate the microscopic distance between these grooves. Diffraction of X-rays actually is very important for understanding distances at the atomic level, for example, in a lattice of a crystal of an ionic compound. One of the magical things about light is that it doesn't always behave like a wave. And here's an example of an experiment that we can do to show that light does not always behave like a wave. When light collides with the metal surface, electrons may be ejected from the metal, and we can actually attract those electrons to, say, a positive plate and measure the current that's produced and measure the resulting voltage. This is called the photoelectric effect, which is a name that makes sense because light is being used to eject electrons from the surface of the metal. Let's investigate the photoelectric effect to determine how the frequency and intensity of light affect the energies and numbers of ejected electrons, and we'll compare the classical wave-like model and its predictions to a model that actually treats light as a particle. Here's the basic setup to observe the photoelectric effect. We have a lamp set to some wavelength and some frequency and some intensity, which is the amplitude of the light wave according to classical theory, a piece of metal that can eject electrons as soon as it feels the light impinging on it, and a plate on the other side to capture those ejected electrons so that we can observe them as a current. This battery is here to potentially counterbalance that current so we can reason about the energies of the electrons that are ejected. So if I start the lamp off here, we can see that as intensity increases, and I'll just show the graph for us, as the intensity increases, the current increases. And that should make intuitive sense. As the light gets more intense, the current goes up. What happens as we vary the frequency and the wavelength of the light? Well, as we go to lower frequencies, look what's happening to the current on the graph. It's decreasing. So we go to higher wavelengths and lower frequencies, from purple to blue to green to yellow. We're getting fewer and fewer electrons, and they're moving more and more slowly. We're getting very little current. And eventually, there comes a point where there's no current left at all. For sodium, for this metal, it's about 490 or so nanometers. What's interesting as well is that point is the same regardless of the intensity of the light. So we can't make the light more intense, I already had it on 100% in fact, and expect more electrons to flow. If we leave it at about that cutoff of 491 or so, we can increase the intensity of the light. And if we look at electron energy versus light frequency, something interesting happens. As we increase the frequency of the light by going, for example, to UV and turn up the intensity, watch what happens to the electron energy. Higher frequency light is associated with higher energy electrons, and in the far UV at 100 nanometers, those electrons are just zipping along massively. What that suggests is that the energy of a light wave is related to its frequency, not to its amplitude, which would have been the prediction of classical wave theory. So the number of ejected electrons does depend on light intensity, but the energies of those electrons depend only on the frequency of the light. And a good way to think about light in the context of this experiment is as a whole bunch of particles. Each particle of light has the potential to knock an electron from an atom in the metal, but it can only do that if its energy is large enough. And its energy appears to be related linearly, like we saw in the graph, to its frequency. So that leads to the relation here at the bottom of this slide, which is one of the most important relations for quantum chemistry, the idea that energy of a light particle, what's called a photon, is equal to the frequency times a constant of proportionality known as Planck's constant. Planck's constant shows up throughout quantum mechanics, and it's very important in the context of the photoelectric effect and in the context of the way light interacts with matter. So let's talk about that now, the interaction of light with matter. When we think about this, actually the particular photon view helps a lot in thinking about how light interacts with matter. A photon has energy proportional to its frequency. We just saw that, E equals h nu. And a photon can collide with an atom or molecule and transfer its energy to it. That makes sense in light of the photoelectric effect, right? That's what was happening to eject an electron from the atom. We say that the atom or molecule absorbs the photon because the photon itself disappears and its energy is transferred into a different type of energy, like the kinetic energy of an electron. On an energy diagram, absorption looks something like this. The atom accepts the photon, which we usually represent kind of with a wavy line and the symbol h nu. You'll see this to represent light throughout chemistry. That causes an increase in the energy of the atom, right? The photon disappears, that had energy E, and that energy has to go somewhere, according to the conservation of energy, right? And that causes an increase in the energy of the atom, which is denoted here with this green arrow. Now, if we think about Coulomb's law, right, this corresponds to kind of pushing the electron outward, right, increasing R. Increasing R causes the energy to become less negative according to Coulomb's law. Remember, E for the atom, for the hydrogen atom, is negative K, E squared over R. So if we increase R, we move the energy closer to zero. We increase the energy. This is absorption. Energetic atoms can also emit a photon and lose the energy of that emitted photon. So for example, if the electron is farther from the nucleus than, say, it wants to be, it can emit a photon with energy h nu. The energy of the, for example, Coulombic energy of the electron being far from the nucleus is transferred into the energy of a photon, and the electron moves closer to the nucleus. This is what we call emission. In the next video, we're going to return to the planetary model and ask, given these pictures of photon absorption and emission, what does the planetary model have to say about the frequencies or the wavelengths of light that an atom can absorb or emit?